Welcome to 4.1, Introduction to Linked Lists. At this point, we've seen that linked lists are an array-based implementation of the list abstract data type, and there's some drawbacks, especially when it comes to inserting and deleting in certain orders. Depending on where you're doing this, it might involve shifting a lot of elements in memory, which could take a lot of time. So in our last example, we saw if you're doing this at the front of the list, it takes time proportional to how long the list is, which is really bad because you have to shift every item by one slot, which can take a lot of time when you have a lot of items. This time, we're going to take a look at a completely different implementation of a list abstract data type that'll attempt to address this. And to do so, we're going to use a new data structure called a linked list. The goal here is we're going to make a class that behaves exactly like the built-in list class, changing only what goes on the private implementation. So that means code like this for each item append to nums, then print, will work whether num is a Python list or an instance of the class we're going to make. We'll even learn how to make list indexing, such as nums3 equals whatever, work on instances of our class. So to do so, we're going to need to understand the concept of links. So the reason why a Python list requires elements to be shifted around is that the elements of a Python list are stored in contiguous slots in memory. Think of like, you literally have just this giant rectangular chunk in there, and that's where the memory is being stored, all connected. There aren't any gaps anywhere in there. But what if you don't have to do that? What if you just have a variable that references where the first element is? Then where are the rest of them, right? That's obviously the problem. And, well, the way that you can solve this is, well, that first element can have a reference to wherever the next one is, somewhere else in memory, which can have the reference somewhere else in memory. And you can basically build a connection of links that link you from the first one to the next one, and so on and so forth. So this bundling of data, an element plus a reference to the next element, suggests something that hopefully is familiar to you. The need for a class whose instance attributes are those pieces of data. And we're going to call this a node. And we'll implement it in Python as follows. You'll note we'll put the little underscore at the front because this is supposed to be a private class in the sense that users aren't supposed to make nodes. They're just supposed to make linked lists. So a node in a linked list is going to be a private class, which means that the linked list class is going to use it in the same program, but clients should not be. And in each node, you have an item, which is the data stored there. Could be anything, a number, a word, so on and so forth. And next, which is the next node in the list. Or if there are no other nodes, just nothing. And so this is where we decide to have those little arrows that follow around to figure out where all the data is. When we initialize a node, given any item, we set the item to be that, and initially, any node isn't going to point anywhere because there are no other ones to deal with. But as we actually add more and more, we can try to build up this little connection here. So an instance of node represents a single element of the list. To represent n elements, we're going to need n nodes. The references and all of their next attributes are what link the nodes together into a sequence. Even though they're not necessarily stored in consecutive blocks of memory, this is why it's called a linked list. So the second class we'll need is an actual linked list class, which will represent the list itself. So this is what we want our clients to be using, and in it we'll implement methods that obey the same interface as the built-in link class. That way we can do things like indexing and so on and so forth. So the first version that we're going to have of this is something really basic. It's just going to have an initializer that creates an empty list. So linked list is an implementation of the list abstract data type. It's going to start out an empty linked list. So the first thing that's there is nothing. Not real fancy. Now, in order to do anything interesting with linked lists, we need to be able to create arbitrarily long ones. We'll see more sophisticated ways of doing this later, but for practice, let's ignore privacy stuff and just directly manipulate things. So we'll make our good friend Linky here. Linky is our linked list, and initially the first element of our linked list is, well, nothing. Now, let's suppose we make 3 nodes, 1, 2, and 3, that have the numbers 10, 20, 30. So the item that's stored by node 1 is the number 10, and the next link from node 1 is nothing. So new nodes don't have any links anywhere. Now we'll manually set node 1's next link to go to node 2. This is like, obviously we're violating a lot of principles here by doing this, which is what we want to avoid in the future, but this is just to sort of show you what will happen as we do this. Node 2's next link goes to node 3. And so now we can say, is node 1's next node 2? Yeah, so it refers to there. If we print the next node after node 1, we're basically printing node 2. If we want to print that thing's item, it prints out the 20, and you can chain these as well, or link them. If we have node 1 dot next, that means you take the first node and move over to the second one, then move over to the third one, and check what item is there. We get the 30. Now, if we want to manually build all this together, we can say linky.first is node 1. So this means set our linked list's first node to be the node. And now we actually have our first item is 10, the next one is 20, next one is 30. Let's actually build this all in Python 2 so you can kind of take a look at how the memory goes as we do this step by step. So let's go with grabbing all this. Again, I'm just going to scratch this out because it complains when I put that in there. We'll grab ourselves a node class. Scrap these because it looks messy. And let's actually just try to copy all of the commands that are done through here. So pardon the fact this may take a slight moment, but it's always good if you want to be able to do this to yourself to know like how can you test this, so you can kind of, I guess, watch me do it. Obviously all these arrows are kind of unnecessary, so we're gonna get rid of them. Also the output lines are kind of useless. Delete that, delete these, delete these, delete these, that, output lines, output arrows, output arrows, output arrows, output arrows. Okay, and then we'll just line up all of the spaces, because Python's really picky about making sure everything is spaced the way that you like it. Okay, and then let's give this a shot, see what happens. Oh, it looks like I crashed something. What did I crash? Right, any is not defined because I'm using an old version of Python where it doesn't like that, so I'm just going to be lazy and delete it, and that should hopefully fix my problem. Get away. Okay, 34 steps. So that means we managed to make it through. Let's go take a look at what happens here. Okay, linked lists don't really have much to them. They have an initializer where they set up their first. And a node also has an initializer, no other methods. All right, we're going to build Linky. Linky starts out with nothing at the start, so we got Linky here. Linky is our linked list that has nothing in it. So if we print Linky dot first, we get none because that's what's here. We're going to build 3 nodes, node 1, 2, and 3. I'm just going to skip through and show you the final thing of it. But here's what we got. So we got nodes 1, 2, and 3. They're over here. Now, this is the important thing. These are not necessarily next to each other in memory. They kind of look like it here because, they're all of these classes and instances are lined up in the order that we made them. But in terms of the way the computer is storing them, these could be all over the place, right? These arrows, who knows where they're going through. But we got node 1 with 10, node 2 with 20, and node 3 with 30. And right now they don't go anywhere, but we're going to change that very quickly. So node 1.item literally means node 1, go over here, print this item out. So you get that. Node 1.next doesn't have anything. But now we're going to set node 1.next to be node 2. This is where things get a little spicy. Oh, look at that. So this is after running the line node 1.next equals node 2. And what happened here is in node 1, that's this thing, instead of having our next node be nothing, we make it so that it points to node 2. And this is node 2. So now we got 2 references that give us to node 2. We can either just directly say node 2, or we can say node 1.next. And now let's do it again with the third node. So we're going to make another arrow here. And look at that. You can kind of already see here we're building this linked list, right? And although the arrows are a little crossing over, which isn't great, you can see we got this sort of chain going on here with our first one. That points to our second one. That points to our third one. And so if you wanted to get to the third one from the first one, you just have to go .next, .next. Okay, so some stuff is printed out. We don't care too much about that. We've seen the output. And now Linky.first is node 1. And now you can see here we actually have a linked list. So our linked list, its first element is node 1, which is this one. And that's why we have the arrow here. So we can get to node 1 by going Linky._first, which basically says go here, follow this arrow, there's what you get. And we can go, linky dot first dot item gives us this. Linky dot first dot next means linky here, first here, next here. Item gives us the 20, so you see it prints out the 20. And then linky dot first dot next dot item says linky first next item gives us the 30. And so that's why we have what we get in the end. Cool. Now, the most common mistake students make when starting out with linked lists is confusing individual nodes with the items in them. So bear in mind, importantly, there's a big difference between node 1, which is this like block of stuff here, and node 1.item, which is literally the number 10. They are not equivalent, right? So as you start writing code with linked lists, sometimes you want to operate on the nodes themselves, especially when you want to move those arrows around. Sometimes you want to operate on the items. Make sure you know which one you're working with so you're not changing the wrong thing. Now, because each element of a linked list is wrapped in a node object, complete memory model diagrams of linked lists can be kind of messy. You saw even here, we got a lot of little overlapping arrows. So here is if you were drawing like the old school MS Paint diagrams of a linked list with 109, 68, 71, 3, and it looks like this messy chunk of things, which isn't very nice and fun to read. I'll definitely argue that this is a little cleaner to look at. So while memory model diagrams are useful for like simple things, and sometimes simple memory errors can happen with linked lists, they can be a little bit overkill when you don't really need that level of detail, right? So here's a couple of other ways you can draw it that look kind of more akin to the Python tutor way of looking at things. Removing all the like types and stuff and extra things you don't need to write. So the first one here is going to keep the item references with arrows, and the second one is going to write the numbers directly in. So we have, this basically the one that you see here at the bottom is kind of what you saw with Python tutor, right? You have linky, which points to here, which is a box that has the number and another arrow, and so on and so forth. Although also this one is kind of accurate as well, where in here is actually a reference to an object that is the number 109. But in the end, these are like effectively equivalent. And honestly, I think this one at the bottom is a much like cleaner and simpler way to look at things that still represents exactly the right information we're trying to convey with these diagrams.